All right, so this class is by special request, and it does feel like one of these topics that we've talked about like a zillion times, but it comes up all the time, and it is probably the most common joke in the field is you have a problem with the system, it's probably a bad TXV. Let's first establish, why do TXVs get misdiagnosed? Why do people always think that it's the TXV? Or why is it that the TXV is often the suspect, usual suspect? Do you have any ideas of why that might be, Carrie?
Low suction pressure.
Low suction pressure, right. That is the most common cause. And so what do technicians typically do? Or I shouldn't say technicians, we'll use that word loosely, but what do a lot of people out in the field commonly do when they see low suction pressure? What's their first response? They grab a tank and they start adding refrigerant to it. Well, on a TXV system, the TXV responds to that by starting to throttle down. And so in a technician's mind, that behavior that the TXV exhibits is a problem. Because I'm adding refrigerant, my pressures aren't going up, it must be the TXV, which is actually the exact opposite of reality. The fact that the TXV is throttling down as you add more refrigerant is an indication that the TXV is functioning properly, is doing its job. So this is a TXV that we did a cutaway on. It's not very dramatic. There's not a whole lot to see. It's hard to do a cutaway on these and actually be able to see anything into it. But let's talk about the different parts of the TXV. So you have the bulb and you have the external equalizer. Now there are some valves that are internally equalized that don't have an external equalizer, but modern air conditioning and refrigeration, you generally are going to have an external equalizer. Easiest way to remember how a TXV works, I call it a constant superheat valve. You know, we have a podcast, in fact, the first podcast we ever did, we talk about the TXV should be called the CSV, the constant superheat valve. And so the TXV has what's necessary in order to measure superheat, just in the same way that what you need in order to measure superheat is you need a gauge to measure the pressure on the suction line, and you need a temperature probe to measure the temperature of the suction line. That's how you calculate superheat, right? With the TXV, it just does that mechanically. When I say mechanically, the actual action of modulating the superheat is done mechanically inside, but it's doing it through pressures. So it's directly dealing with pressures. It's not converting it to a temperature and using a PT chart or a gauge. It's just directly comparing these pressures, and by those pressures, by those mechanical forces, it maintains superheat. So it's measuring the temperature of the suction line at the outlet of the evaporator. It's measuring the pressure of the suction line at the outlet of the evaporator. And then it also has a spring pressure, which in some cases is adjustable. In the case of this valve, it wasn't adjustable, but you can take the end cap off and you can adjust the stem in order to affect that opening and closing. In this particular case, the spring pressure adds a closing force in addition to the external equalizer. So the external equalizer is a closing force, the spring is a closing force, and the bulb is an opening force. You know, one of the earliest things we talk about in air conditioning refrigeration, pressure-temperature relationships. You know, you increase the temperature of something, you also increase the pressure. You decrease the temperature of something, you also decrease the pressure, right? You have a fixed amount of refrigerant in this bulb. So there's a fixed mass of a refrigerant charge in this bulb. And so if I heat up this refrigerant that's in this bulb, then it's going to exert greater force. And since this is the opening force of the expansion valve, the bulb pressure is what causes the valve to open. The hotter I get this bulb, the more it's going to drive the valve open. And so that's why a lot of technicians will say, you know, pull this off and warm it up with your hand. You know, that's a common thing that they'll say. You know, how do you test the TXV? Oh, I pull the bulb off and I warm it up with my hand. That's all fine and dandy, but what a lot of techs will do is they'll go to a job and it's got low suction pressure. When we're talking about this very practically, I'm going to try not to go too technical here and just make it like real world. They go to a job that's got low suction pressure. They say, well, I heard that what I should do is pull the bulb off. So they go and they disconnect the bulb and they warm it up. They go look at their gauge and they might warm it up and run outside real quick. They might put it in a glass of warm water. They might, I've even seen some guys heat it up with a torch. Don't do that, but I've seen guys do that. Use a heat gun, stick it outside the cabinet. They do all kinds of things. And they go outside and their suction pressure goes up. Well, what determination do they make based on that information? So they did a test, but they did a test not knowing what the outcome of the test should be. With a functioning valve, your suction pressure is going to go up slightly under most load circumstances. If you were under really high load and, you know, again, you were measuring it wrong or something, then that could cause a problem. But we're assuming that our suction pressure is low. And so you're warming it up in order to drive your suction pressure up. And a functioning valve, when you do that, your suction pressure will go up. Because, and also your head pressure will also go up a little bit too. It won't happen instantaneously, but what is happening when you warm this bulb up, because this bulb is the opening force, the valve goes open, allows more refrigerant into the evaporator coil. When you allow more refrigerant into the evaporator coil, the refrigerant density in the evaporator coil increases because you got more of it, right? Suction pressure goes up, you have more refrigerant getting back to the compressor, so now your head pressure is also going to go up on the other side. So it kind of creates this, increase in pressures all the way around, generally speaking. Now again, if you just do it for a couple seconds, you may not even notice it. But because this is the opening force, that's what should happen. Now let's say it doesn't happen. Let's say you go and you heat up this bulb and nothing happens, because this is a diagnostic tool that all you guys use too. Well, it could be that the bulb has lost its charge. That could be because this bulb is the opening force for this valve. It could be that this bulb is no longer exerting that force on this valve. And in some cases, these power heads, just this top portion here, can be replaced by itself without having to replace the entire valve, especially in commercial refrigeration, large commercial, those sorts of applications. So you want to know the difference. And generally speaking, you can kind of tell. And I know this sounds sort of weird, but a bulb that has no refrigerant in it, it has kind of a different sound to it. It has a lightness to it. You can kind of tap on it and you can tell that there's no refrigerant in it. Again, that's a feel thing. It's really hard to demonstrate. I should probably take two and show the difference. Good idea for another video. But you can generally tell when it's lost charge. Sometimes you can see the fact that it's lost charge. You can see the fact that there's a crack or something in the line. At that point, you can't recharge it. And I've seen guys, there's all kinds of crazy strategies out there to get TXVs working temporarily. I've seen guys drill holes into the side of the bulb and put a Schrader in it and try to charge a little refrigerant in it. I've seen guys do it with nitrogen to drive the valve open. And for temporary operation, sometimes you got to do weird things. But in most cases, where the charge has leaked out of your bulb, you got to replace the whole power head or the valve, depending, whatever the case may be. That is your opening force. So when you heat it up, you would expect to see it go open a little bit. The problem is that how much should it go open? Well, you don't really know. So you're going to heat it up, and so a lot of guys will say, well, it went up a little bit, but it didn't go up that much. Still replace the valve. So the point I'm going to kind of get to is that test, while it doesn't, maybe has a little value, it isn't a very valuable test. Not the first thing that I do. I'm not going to go and grab the bulb and heat it up. That's not the first step I'm going to take. So we're going to get down to how you actually do diagnose this. Opening force is the bulb. Closing forces are both the external equalizer and the spring. If you have bulb pressure, but you don't have the closing pressure, it's going to go too far open, which can happen in a valve. More uncommon, but can happen. And, well, I shouldn't say more uncommon. There are cases, like we work with large grocery store refrigeration, and we set a case, and when you set the case, you've got to set the superheat on that valve. And so in a lot of cases, those evaporator coils may be flooding back because the TXVs are too far open unless you set the superheat. We're generally talking about residential air conditioning, and wherein the valves are set from the factory for that unit, and there's very unlikely that you're going to need to adjust a TXV. And so it's very unlikely that you're going to need to adjust one, especially for it being too far open. That's just not a common thing that's going to happen, but it can happen. Spring, external equalizer, bulb, the balance of those forces is what causes this to be a constant superheat valve. That's its job. Okay, so if its job is to be a constant superheat valve, then our job is to make sure that it can do its job, first and foremost. So it's got to have some things in order for it to work properly. The first is it's got to have a full line of liquid coming in. If it doesn't have a full line of liquid coming in to the valve, then it's not going to be able to do its job. And so how do we tell if it has a full line of liquid? Subcool. Subcool is how we tell. You're working on refrigeration, you may have a sight glass. Sight glass gives you that same sort of indication. A lot of people wonder in refrigeration why you don't measure subcool as much or why it's not as important. You can measure it, but as soon as you have a receiver that's in the circuit, that kind of changes things a little bit. So in most cases, refrigeration technicians are clearing a sight glass. That's how they're thinking of it. But saying clearing the sight glass and saying having a proper subcool, those are kind of the same thing, in the same category. The idea is that this is the metering device. Its job is to create a proper pressure drop and a proper feed of refrigerant into that evaporator coil, and it has to have a full line of liquid coming in. If you ever go up to the unit that's making the sound, that's an indication that you have some vapor in that liquid line. It doesn't matter what your subcool is outside. If you hear that coming into your valve, you still have vapor in your liquid line, and that can happen because of restrictions, restricted dryers. It can happen because of long line length at high temperature. Anything that can cause that refrigerant in the liquid line to lose its subcooling, to start to become vapor again, pressure, temperature, line length, all those things are impacts on that. And so if you're not feeding your expansion valve with a full line of liquid, that can cause it not to do its job. And I'm just saying this because there's two different categories of misdiagnosis on TXVs. The one category is a complete misdiagnosis misunderstanding of how it works. And that's the whole, well, my suction pressure is low, so I replaced it. There's no reason for that one. The other one, which is a little more tricky, is that let's say this has a, some valves have this one doesn't, but let's say it has an inlet screen. And so that inlet screen is actually where the restriction is and not the body of the valve. The body of the valve inside here, the actual seat where the refrigerant goes through, that's supposed to be a restriction. It's designed to be. It's a pressure drop device that maintains constant superheat. But let's say there's a little restriction here. If this restriction here is not allowing the correct amount of refrigerant to actually hit the valve, then the valve may be doing its job and the problem may be in that inlet screen. And so we've got to do everything to make sure that this valve is getting the proper amount of liquid refrigerant coming in. It also has to have a proper pressure drop. Now, we live in Florida. In Florida, we run air conditioning most of the time when it's pretty hot outside. And so we don't have a big problem with this in residential, but there are cases where you may be running air conditioning and it may not be very hot outside. And this especially comes up in refrigeration. In refrigeration, you could be running, freezers inside of a grocery store and it could be, negative 20 degrees outside. And you still need to run those freezers. And so when we are exchanging heat to the outside air, that's where we exchange our heat to in our condensers. And that outside air then has a lot of control over what our pressure is. And so unless we can keep that pressure up high enough, about, generally speaking, and this varies, but about 100 psi higher than your desired evaporator pressure, then your TXV will also lose control. You need to have about 100 psi pressure drop. Again, in most cases, that does vary. And with electronic expansion valves, they have a little more control even. But you need about 100 psi differential. And so where that comes in, why that matters, is when your outdoor ambient conditions drop. Or let's say you're using water in a water-cooled condenser. If your water temperature got too low, for example, or your flow rates were too high, where you didn't have high enough head pressure, then that could cause your TXV to lose control. You have to have a full line of liquid. Your head pressure has to be high enough. Now, that head pressure being high enough thing, that doesn't come up a lot with what we do in residential. Because again, if you're running air conditioning, in most cases it's hot outside. That's why you're running air conditioning. So that shouldn't be a problem. But in certain cases that can come up. In commercial, it can come up. You could have a space where you're running air conditioning and it could be 50 degrees outside. The general rule is for typical air conditioning with no specialty controls, you really can't run air conditioning when it gets below 65 degrees outside. So typical residential air conditioning, stuff we work on every day, if it gets below 65, then you're going to start losing control over that difference between your evaporator pressure and your liquid line pressure, the pressure coming out of your condenser. So here's where the rubber meets the road. Suction pressure is low and they don't know what to do about it. When that happens, now we've already determined suction pressure is low. The next thing the technician should do, measure superheat and subcool inside and outside. Practically speaking, on a residential split system, what that means is you take your subcool and superheat outside, but you pay attention to what your line temperatures are outside. I measure my superheat outside, we'll say it's 10 degrees of superheat, okay? And my suction line temperature is, we'll say, 50 degrees. 50 minus 10 is 40. That means my suction saturation is 40 degrees. Okay, so because 40 plus 10 degrees of superheat equals that suction line temperature of 50. Subcool outside at a liquid line temp of 95 degrees. That means that our saturation is 105. These are pretty typical types of numbers that you'd see on a mild summer day. This is my outside. This is what I've got outside. So I've got 95 degree liquid line outside. I've got 50 degree suction line outside. Now I go inside and my suction line temperature is 47 degrees and my liquid line temperature inside is, we'll say it's 93 degrees. So the temperature of the suction line increased from inside to out by 3 degrees and it dropped from 95 to 93 traveling inside. Okay, that's very realistic for our environment. We run these copper lines in chases underneath buildings, and you're running a liquid line and a suction line in together. Even when you insulate them, sometimes it gets water in there, so there's a little bit of heat transfer. Now, I would rather see these two numbers be the same. I would rather see these two numbers be the same. That would be my preference, but realistically, that's not always going to be the case. This is an indication, if I were to see this under normal circumstances, this would not be an indication of a problem. I wouldn't think to myself, oh my gosh, I've got a restriction, I've got a line dryer, I've got a kinked liquid line or something, I've got something weird going on. This would be about what I would expect to see. Because it started off at 47 degrees inside, which means that now my inside superheat is 7 degrees. My inside subcool is 12 degrees now. It went that way versus the other way. Now, that's tricky because I don't know what the pressure is inside. And so that temperature could have dropped just because it gave off a little more heat inside the chase, or that temperature could have dropped because there's a kink or something, and now my pressure dropped, and that would mean that the subcool that I'm assuming is incorrect because, again, I'm measuring my pressure outside and I'm measuring my temperatures inside. So that could be a problem, and that's why I'm still listening. When I go inside and I listen to that liquid line, I'm listening to hear, am I hearing that sound? Because again, it would be beautiful if I had a port, then I could just check my superheat and subcool inside as well, but I don't have a port, so I have to kind of just go off of what my pressures are outside. So there's always the possibility for a kink or something, not very common. And generally, if you have a line dryer, you can just measure the temperature across the line dryer. That's another common cause. Technicians will misdiagnose TXVs because of restricted line dryers, restricted inlet screens, and then because of airflow, which is what we're going to talk about now. So I checked this, that's all okay. Now, let's say that I run into, because this is a pretty typical circumstance here, but let's say I run into something that's a little bit more insidious. Let's do R410A. Let's go with what we would consider to be a low suction pressure, because again, this is the first indication that a technician would have that, oh, I think something's wrong, okay? Let's say we run into a system and the suction pressure is 105 PSI. 105 PSIG. So make sure that you're on the gauge scale on that app. 33.6 degrees, and we call that suction saturation. My preferred term for it would be evaporator temperature. So we have a 33.6 degree evaporator temperature. That's the temperature of the boiling refrigerant inside the evaporator. That's lowish. So let's say that the inside temp is 75 degrees. We should see, in general, under most circumstances, 400 CFM per ton type of circumstance, about a 35 degree difference between the indoor temperature and the suction saturation, otherwise known as the evaporator temperature. You can see we have more than that. 75 minus 35 is 40, so we're 6.4 degrees low from what we think that we should be. While this isn't way out of bounds, it's definitely low suction pressure. A technician who's been around long enough to hook gauges to a couple things is going to say my suction pressure seems low, and this is where things start to spin out of control as far as the TXV goes. It's close to freezing, right? So that's a good indication. That's a good thing to have thought. And because you even get a more junior tech, they may not even perceive that they're close to freezing. But at least you get to the point where it's like, all right, that's close to freezing, that's not good. Okay. So now, what is the next step that I take? Most technicians are going to go, and I shouldn't say most, but a lot are going to go and they're going to go for their tank. They're going to say it's low, they're going to quote the customer, whatever, I got low suction pressure. That is not the next step. The next step is to go ahead and get the rest of the 5 pillars that we talk about. Superheat, subcool, air temperature split, suction pressure, head pressure. Those are the standard ones that we do, and there's a lot more than that even. But we're going to start with that. So my suction pressure is low. The first thing I'm going to do is check my superheat and subcool outside. So let's say my subcool outside is 12 degrees, and my superheat is 14 degrees outside. So a lot of technicians are going to look at that. They're going to say, well, 14 superheat, I mean, that's not real high, but it's a little high. Maybe I have a bad TXV. TXV's job is a constant superheat valve. Maybe I have a bad TXV. So they're going to get that seed of thought in their mind. I can tell you, this is not a bad TXV. This is not a bad TXV. If it was a bad TXV, meaning failed closed, because that's what we're saying. Techs also get failed closed and failed opened confused. Failed closed means underfeeding. It's not allowing enough refrigerant into the coil. That's what we're looking for here because we're saying that we have low suction pressure. Low suction pressure means that if it was the expansion valve, it would mean that the expansion valve wasn't feeding enough refrigerant into that evaporator coil. 14 degrees superheat is an indication that it is not underfeeding significantly at all. It would be definitely higher than that. Because again, where did we measure this? We measured it outside. That's where we always measure it first, because where we hook our gauges up. So now I go inside, and I remeasure my superheat, and I see that inside I have a 10 degree superheat. This would be very typical. It's had the chance, as it's run from inside to out, for it to pick up a little bit more superheat in that chase or whatever the case may be. I mean, it depends. Obviously, if you've got a line set that's 4 feet long, then you're not going to see a big change. You shouldn't see a big change. But if you've got a line set that's running through an attic or it's going through a chase and it's 50 feet, you're going to definitely see some change in temperature. So now inside we have a 10 degree superheat. Well, that's right where we want to see it. What I generally say in residential air conditioning is 6 to 14 degrees of superheat at the evaporator coil. That's about what you're looking for. Now again, if you test 50 of them, more of them are going to be in that middle range, more like 8 to 12. That's going to be, but sometimes there's a little bit of variation. And I don't want technicians condemning expansion valves over a couple degrees of superheat, because the truth is your tools generally aren't even accurate enough for you to be sure within a couple degree range. You could be reading 10 and it could be 8, or it could be 12. easily, even with the good quality tools we use, let alone some of the tools that some people are using. Because superheat is a comparison of two numbers, both of those numbers have a range. That means that you can be a little off one way or the other. We're just looking at this situation right here. Inside temperature 75 degrees, 105 psi, which equals a 33.6 degree evaporator coil. My subcool's 12, my superheat's 14. There's other things that I need to check here. I need to actually show you the head pressure and split and all that stuff, but I can pretty much tell you right now, I got an airflow problem. How do I know that? Because my suction pressure's low, meaning my evaporator temperature's low, and my superheat is in range. It's not high. Now let's look at this same circumstance, and now we change this outdoor superheat number to 27 degrees. And I recheck it inside, and it's 23 degrees. Now, a couple more things I gotta check. I gotta check that whole inlet screen thing, make sure that couldn't be it. I gotta make sure that I have the subcool not just outside, but inside. I've gotta make sure all that stuff. But once that's all checked, and I know that I have enough pressure coming in, so I got that 100 psi headroom between evaporator and the inlet, I've got subcool coming in, now I can condemn the TXV. Because TXV starts at the inlet of that evaporator coil, and it's tied into the outlet of that evaporator coil. That's what it's controlling. And so if I'm measuring superheat at the outlet of that evaporator coil, and it's high, which from a practical standpoint means that I'm measuring a high suction temperature in relationship to the pressure, the evaporator temperature, right? Pressure converted to an evaporator temperature on the suction side. If that is high, that difference is high, then that means that the metering device, the TXV in this case, is underfeeding. It's not feeding enough refrigerant through that evaporator coil. If it was correct, meaning it's in that range of 8 to 14 or 6 to 14 that we talk about in residential air conditioning. Now again, the refrigeration guys always freak out on me because it's like, oh, it's different refrigeration. I get that. There are some, you can run very low superheats, 4 degrees superheats, 3 degree superheats in some cases even on ice machines or things like that. But air conditioning, we're really going to be more in that 8 to 12 in most cases. But that's at the outlet of the evaporator coil. We've confirmed that. We've confirmed that we have what we need going in. Now we can condemn that TXV. When guys misdiagnose TXVs, and because in a lot of cases they'll say, I checked the superheat. Well, maybe you checked it outside. Maybe you didn't recheck it inside. Maybe you didn't let it run long enough. And so your superheat didn't have a chance to settle in because you were being impatient with it. You saw a high superheat, but you only let the system run 5 minutes. Superheat takes a while because it has to go, that refrigerant has to go all the way through the circuit, and it has to cool down all of that mass, all the thermal mass of the evaporator coil, and then all the thermal mass of the suction line for you to actually measure that superheat. So you gotta let it run for a while. The other reason that a lot of times guys will condemn a TXV when they shouldn't is, my superheat was in range. Well, their tools aren't measuring properly. So that's another reason, commonly. But their gauge is reading low. They didn't calibrate it. They didn't zero it out to atmosphere. I mean, even Testo 550s, which are my favorite set of manifolds, you have to zero them out. You have to open them to atmosphere, hit that zero out button so that way they reset. And you gotta do that every time. Otherwise, you could be significantly off on your pressures because it recalibrates, and it will recalibrate with pressure under it, and it can be really wrong. Same thing with analog gauges. Obviously with analog gauges, you could be 4 or 5 degrees off very easily. And so you thought that you had 14, or you thought you had 19 and you actually had 14. And you're like, well, 19's high, but you didn't actually have 19, you had 14, and 14's acceptable. You understand? This is where guys who are even good technicians misdiagnose expansion valves, even understanding that it's a constant superheat valve. 27 degrees superheat and 14 degrees superheat, that may seem like a big range, but that's only 13 degrees difference. And that's the difference between a failed TXV and a good TXV. The main thing to know about a TXV, though, is it's a constant superheat valve, and its job is to feed the proper amount of refrigerant into that evaporator coil. And the way that it knows the proper amount of refrigerant to feed into that evaporator coil is based on the superheat at the outlet of that evaporator coil. Bulb is the opening force. External equalizer is the closing force. Just like Jesse mentioned, why do you need to pull that bulb off and warm it up? Well, if you're measuring superheat and subcool accurately, I don't really see a reason. The only reason that I can see is that once you have already diagnosed a valve as being failed closed, meaning it's not feeding enough refrigerant through, you can do what they call exercising the valve, which is just a matter of driving it open, letting it close, driving it open, letting it close. And sometimes that varnish or whatever is built up in there, whatever gunk's gotten in there can free up. We work in a heat pump market, which means, Probably 80% of the equipment we work on in residential are heat pumps. In a heat pump market, you don't need to do that. Just run it back and forth in heat to cool, because that's going to do a much more effective job at exercising that valve than heating it up with your hand. So that's how you exercise a valve in a heat pump market. Now, either way, it doesn't necessarily solve the problem. You got it open maybe. I mean, I've done that a couple times where I've gotten a valve to free up and now it's working properly. But did you really fix the problem? In those cases, I'm probably still going to recommend replacing that valve and then definitely changing out the line dryer. Because my concern is what got into that valve. Answer: byproducts of moisture, so you get some, all sorts of acids and crap from moisture because the proper evacuation wasn't pulled. And then also carbon, if they didn't flow nitrogen while brazing, that can get in there. There's a lot of things. There's the whole issue with the oil additive thing that happened a few years ago where the corrosion inhibitors got in and messed up valves. So there's a lot of things. Valves are very sensitive. They're one of the more sensitive components on the system because the job that they have to do is very fine. It's a very detailed job that it has to do. Having said that, TXVs do fail. So the joke that it's never the TXV, it's actually always airflow. No, a lot of TXVs they do fail. Now, why do they fail? There's a range of different reasons. Rub outs on the bulbs and vibration and all that. And we see certain brands that definitely fail more than others. We every winter on Lennox heat pumps, we go through all of these heat mode expansion valves, and it's just the way that they're installed makes them more prone to fail. On the external side, things that we allow in the system: moisture, carbon, those sorts of things, dirt, because you ran the line set and some dirt got in it or whatever, those are obviously going to have the tendency to get in valves and plug them up. So we want to find the cause as much as possible, but that's the only, when we talk about exercising the valve, that's the only case that I can see actually pulling a bulb off and doing that is on a straight cool system where I'm wanting to try to exercise that valve. I'm wanting to try to maybe get it open, or maybe to try to temporarily get somebody some air conditioning. If I can take the bulb out and stick it outside the cabinet a little bit to drive up the suction pressure, get it out of that freezing range. Again, that only applies if your superheat is high. If your superheat is low, you don't want to drive the valve open. Driving a valve open when superheat is low is going to flood back to your compressor. You don't want liquid refrigerant going back to your compressor. And so if you have low superheat, you do not want your valve to open more. If you have low superheat, you do not add more charge. This is just a quick real talk absolute statement. If you have low superheat, do not add more charge. That does not solve anything, because what that low superheat is telling you is that your evaporator coil is already fully fed. Adding more refrigerant to it is not going to fix any problems. It's only going to make problems worse. And a lot of guys are constantly saying, well, but I had to get it out of the freezing zone. It depends geographically, but overall, the whole range, most cases of freezing are caused by airflow. That's a more common cause. Dirty air filters, improperly sized ductwork, somebody jamming a filter inside of a return grill, somebody shutting off a whole bunch of vents inside the house because their kids went to college. Whatever, anything that reduces system airflow below that desired system airflow. Really, anytime you're getting below 350 cubic feet of air per ton on a regular basis, you're going to run the risk of freezing. That's what you want to look at first when you're talking about low suction pressure, if it's accompanied by normal or low superheat, not adding charge. It should be a very rare circumstance that you're adding charge in order to see what happens, because you already know what is happening based on superheat, subcool, all that. The one exception to that is when you really do have a restriction. When you really do have a bad restriction, sometimes it can be tough to find. Now, in most cases, we know the common areas that restrictions happen: check valves, metering devices, solenoid valves, filter dryers, those sorts of things. That's where you're looking. But when you do get a real bad restriction, then some weird things occur in the system, because and this is a total aside, but I want to just mention this here because this comes up sometimes. If you do have a restriction, guys expect your head pressure to go up. That's what they imagine, because they imagine this compressor as a pump that's pushing against a restriction and the head pressure going up on the one side and it dropping on the other. But refrigerant is very dynamic and it changes state between liquid and vapor. And so if that theory were true, this is just the easiest way to remember this. If the theory were true that a restriction caused high head pressure, what would happen every time you try to pump down a system? Close off the liquid line, right? First, and it pumps everything into the condenser. Well, closing off the liquid line is 100% restriction. So if you did that and that causes really high head pressure, my goodness, you should blow your condenser sky high, right? But that's not what happens. What happens is that as it gets packed into that condenser and the heat keeps getting rejected off of it, it just turns into liquid. As long as you don't overfill it. Now, you get to a place where you get to 100% full of liquid, well, now you get hydrostatic pressure, and yes, you will explode it. And we see that in some cases with microchannel coils, because they don't have as much volume inside of them. But in a traditional unit, we're pumping them down all the time, right? No problem. Your head pressure's not going sky high. And that's because there's enough space in that condenser to hold all your refrigerant. You know how you know? Because it gets shipped to you with all the refrigerant in it. So we know that it's designed to hold all that refrigerant. The reason that your head pressure goes up is because heat is being transferred and rejected. Because you actually have heat coming down your suction line that's ending up in your condenser, and now that's what's driving your head pressure up. So when you have a big restriction, this is the point, have a big restriction, your head pressure will actually go down. When you have a TXV that's throttling back or is underfeeding the evaporator coil, your head pressure is actually going to go down. And that throws some people off because they will walk up to it, and what do they see? Low suction pressure, low head pressure, I'm low on charge. Right? That's what they think. And that's why you can't just walk up to a system, low suction pressure, low head pressure, I'm low on charge. Within reason. An experienced technician can. You walk up to that system, it's an R410A system, you hook up to it, oh, I got 60 suction and 150 head. Okay, you're low on charge, right? I mean, so there's a range to all this stuff. But when you see a circumstance like this, oh, my suction's a little low, and this is where it always happens, it's a little low, ma'am, I'm gonna add a little charge for you, right? That's where, no, you gotta check your superheat subcool, you gotta let it run long enough before you can make that determination. Hopefully we don't misdiagnose. Two things I forgot to mention in the class. One is whenever you have a low superheat, so you're operating the system, it's run for a while, and you notice that you have a low superheat, one thing you should watch for is how well this bulb is connected to the suction line. If this bulb is not well connected, it should be connected generally with like a brass or copper strap, very snug on the line. Position can matter in really large lines. In general, residential, light commercial, maybe small refrigeration applications, it doesn't matter so much where the bulb is positioned on the line, so well as it's really well strapped to the line. And then you need to make sure that it's insulated in most cases. Now, some manufacturers don't insulate them. In general, not insulating is going to result in a slightly lower superheat. So if you're in a range where that's a problem, then you may want to re-insulate. I recently insulated a factory bulb on a TXV and it increased the superheat by about 3 degrees. So it does make a difference, and that is something, if you're running too low a superheat, that you might want to look at. Another thing to watch out for when you have a valve that's not metering properly is whether or not it has one of these 1/4-inch flare connections at the inside. If you use a 1/4-inch flare connection, that's fine, but just recognize that most of these don't have core depressors in them. So when there's no core depressor inside this flare, you can't have a core in that port. So you have to make sure that core is out of the port. Otherwise, you won't feed through pressure and you won't have that appropriate closing force like you're supposed to have from that external equalizer.